Hi everyone, this is Group 15, Section 04's presentation, and our title is The Impact of Road Conditions on the Number of Accidents. As we all know that road transportation is unavoidable, and this being said, safety on the roads plays important roles. The data sets we are using for this study was gotten from the Adams State Department of Transportation, and it includes variables or predictors such as number of average daily trucks, average annual daily passenger traffic, and the likes. In this research, we aim to investigate correlation among the various variables on the number of accidents. For example, the traffic conditions, pavement conditions, and road geometric conditions as being presented. This is our general research question. Do various traffic, pavements, and geometric road conditions have a significant impact on the number of accidents? These are variables as follows and as follows. The first research question is that do traffic conditions impact the number of accidents? We made use of three explanatory variables, one categorical variable included, making four, and our response variable is the number of accidents. Our research question 2 is based on pavement conditions, all continuous variables, and our research question 3 is based on geometric road conditions on the number of accidents, also all continuous variables. For our research question 1, this is making use of a linear mixed model in order to ask or to check for the impact of the following traffic conditions on the number of accidents. This include average daily truck volume, average, which is AADT, speed limit, and traffic wave flow on the number of accidents. We use a sample size of 5,679 after different data cleaning measures have been done. So first off, we want to use some preliminary analysis to examine assumptions violations, which include non-linearity, non-normal distribution, non-constant variance, multicollinearity, and the presence of potential outliers. In order to check for non-constant variance and non-normality of errors, and we find that the residual versus fitted plot shows non-linearity and non-constant variance, and the Shapiro plot along with the normal quantile plots shows that we have non-normal errors. We went further to use Brown-Forsyth test, heteroscedasticity test, to confirm the non-constant variance, and we find that it is truly non-constant, and our box plot for speed limit shows a potential outlier. The box plots for the other predictors, which are not shown here, also shows diverse outliers, and it's included in the write-up. So examine multicollinearity between all of the predictors we used. We found that there are no visible multicollinearity. However, we state that is inconclusive as our data set happens to be large and the plot is really inconclusive. This is our initial multiple linear regression model, and it includes interaction terms between the categorical variable and all other predictors in the model. These are remedial measures for non-constant variance and non-normality of errors. As we found that we have non-constant variance and non-normality, we decided to use Box-Cox procedure to transform Y. We obtained the highest lambda of -3, and then we applied it for transformation. Our Brown-Forsyth test after transformation also was statistically significant, indicating non-constant variance. Our normal quantile plots still did not change a lot. However, this was our new model after transformation. In the model building procedure, we have the following, and model 6 and 8 happen to be the most ones that fulfill certain criteria. However, we proceeded with the stepwise regression and the k-fold validation, and we decided to go with the full model. We proceeded with the added variable plots to see if we can drop some model, as we were still not sure with what we got from the previous best subsets, and we decided to drop some models. This is our final model. In order to check for some outliers and influential points, we see that we have different outliers and different influential points, and also we have outliers on X, outliers on Y. And according to Cook's distance, this is our major influential points on case 4918. We did not present our DF beta plots as we found that there were a lot of cases that have potential influence on the model. This happens to be a great bias for our study. Once again, we check multicollinearity on the new model using the VIF tolerance values. We found that we have multicollinearity between the following values that have a greater than 10 value. We try to perform a remedy for non-constant variance or heteroscedasticity using the weighted least square method. As we can see, after performing weighted least square, our errors appeared normal and our histogram also appeared kind of normal, and also our F statistic increased in the weighted least square as compared to the ordinary least square. However, our x3 variable and our x4, x41, x3, x42 variables lost their significance in the weighted least square method. This is also an indication that our weighted least square method improved the model. And in summary, we found out that weighted least square improved our model. A final model after bootstrapping is this. This is actually the best regression model to answer this question. And we conclude that average annual daily traffic as seen in the ANOVA type 2 tests it has the most impact on the number of accidents. Thank you.
Here is research question 2, and we wanna consider and investigate the impact of international roughness index and Rotterdam besides of pavement condition rating on the number of accidents. This is an initial MLR regression model that shows the impact of our x5, x6 and x7 on y, which is number of accidents. As you can see, this is assumption checking for residual plot, and it shows there is non-normality and non-constancy between the variables and fitted values. To figure it out, we decided to do Shapiro test and Braun-Forsyth test. So as we guess, the result is a non-constant variables and regarding p-value and graphs. So we decide to solve this by transforming y using box cost. Here is a box cost, and we see the value of lambda is the biggest log likelihood around 3. Here is a box cost result, so we should double check normality and constancy of variance again to see whether transforming y solved that or not. As we guess, it doesn't solve and still there is assumption violation between variables. Then we are going to check multicollinearity, and this shows there is a low correlation between variables, so we are not worried about a multicollinearity between variables. Here we wanna figure it out, can we drop off one variable from the model? So as the result shows, there is a F statistic is bigger than F critical, so we can figure it out. All variables are important and meaningful, so we cannot drop off any variable. Here we are trying to find out the best subset selection. So as the model shows, we decide between first and third model. We decide by k-fold and the lower RMSE, which is a third model. So this model would include all the variables because all of them are meaningful. Here we are trying to find out influential points and outliers, and after we figured out outliers for x and y, we remove this and we clean our data. Here we were trying to check VIF and multicollinearity again after removing data, and it shows this value also sounds good. From this slide, we will find out that all variables are important given the other predictors are already in the model. Finally, we decide to use a weightless score regarding our non-constant and non-constant and non-normal variance. As this slide and residual plot shows, the estimated errors has been reduced. Here's a slide after bootstrapping, and this here is our final model.
In our research question 3, we aim to investigate the impact of different geometric road condition variables on the number of accidents. The predictors in this question are the number of length, the median width, the interior shoulder width, outside shoulder width, as well as the number of horizontal and number of vertical curves. In the null hypothesis, we hypothesize that all betas will be equal to 0, and in the alternative hypothesis, we expect that at least one of these betas are not equal to 0. So we ran the MLR model. We found that the F statistic is greater than F critical, and hence we reject the null hypothesis and conclude that not all betas in this question are equal to 0. And we have a preliminary MLR model that is presented on the screen. In order to check assumptions, we ran a Shapiro test in order to test normality of errors, and we also tested for non-constancy of variance, and we found that both assumptions were violated. Errors followed a non-normal distribution, and there was a non-constant variance. So now we would try doing transformation on Y in order to fix these assumption violations. When we did Box-Cox transformation on Y, this did not fix our assumption violations. Both the errors stayed non-normals and the variance stayed non-constant, but it also has led to the shrinkage of estimates to almost 0, so we stick with our original model. We did not use the model that we obtained after transforming Y because it wasn't helpful. We did not find multicollinearity between the different road geometry related variables. As for the model selection and k-fold cross-validation for the candidate models, we had 2 candidate models. The first one is model number 2, and in this model all the predictors are dropped except for the number of lanes and the median width. And the other candidate model is model number 5, in which only the number of vertical curves is dropped. So, and after running a k-fold cross-validation to choose which of these 2 models are the best, we found that model number 5, which only drops the variable or the predictor x13 or the number of vertical curves, we will proceed with this model. So in model number 5, which we chose as the best subset, all predictors in the subset is significant at a significance level of 0.1. There may be outliers in the model, however, they are not influential according to the Cook's distance values that we got. The outliers present in this model may be explained as a result of the non-normality of errors or the non-constancy of variance. So the model so far is described by this equation. So in order to reduce the problem of inconstant variance, we performed a weighted least square followed by bootstrapping, and we found that running the weighted least squares has led to the increase of F statistic from around 61.8 to 210, and the R square adjusted almost tripled from 5% to 15%, and the residual standard error decreased as well. So after performing bootstrapping on the weighted least square model, we reached our final MLR model, which is the one presented here down the screen. In research question 1, in which we aim to study the impact of road traffic conditions related variables, we found that the weighted least square method has greatly improved the model, and we also found that the average annual daily traffic variable was the most impactful among all the variables in this question. In research question 2, we found that all 3 variables related to pavement condition were impactful, and their impact was almost similar on the number of accidents. For research question 3, in which we aim to investigate the impact of geometric road conditions related variables, we could confidently drop the number of vertical curves variable, and a more parsimonious model would be one that drops the interior shoulder breadths, the outside shoulder breadths, as well as the number of horizontal curves variable from the model. However, we decided to retain them on the model because they were not dropped during the model selection and the validation processes. However, it is very clear that the number of planes, which is x9, and the median width, which is x10, are the most impactful in this question.